slide deck. Okay, so hi everyone. Thank you for joining me today, and thanks Jeff for having me in this very great event. My name is Matan Jungman. I'm the CTO of Madeira Data Solutions. We're a consulting company based in Israel, but we provide our services worldwide, and we deal with everything around data. A lot of it is SQL Server, but we also deal with other technologies. This is my email. I'm also on Twitter. My blog is at madeira.data.com/blog, and I also have a podcast where me and Guy Glanzer geek out about SQL Server, and we release a show every 2 weeks, and we have a lot of fun, and it's a great way to learn wherever you're at, whether you're commuting to work or jogging or washing the dishes and so on and so on. So give it a try. So we're here to talk about Columnstore indexes, and this is a technology that fascinates me, and it doesn't fascinate only me, it also fascinates Microsoft. They invest very big money in this technology, and one of the reasons it fascinates me so much is that the traditional SQL, the traditional data structures in SQL Server were developed at around 1995. That's about 20 years ago, and a lot has changed. And we're here to talk about the changes that happened since then. And one of them is Columnstore. So let's talk about the agenda. We'll talk about what is Columnstore, how is it built, what is it good for, and how to make your benchmark successful. And what do I mean by making your benchmark successful? Most probably, most of you won't go and put Columnstore in production tomorrow. What you will do is go ahead and start playing with it and starting to benchmark whether your system can benefit from Columnstore. So we will talk about a few things to keep in mind when performing this benchmark. And we'll also talk about the future, which is SQL Server 2016 and on. So the traditional approach, and as we said, was developed at around the 90s, was raw store. We didn't know what raw store was until Columnstore came in, but now we call it raw store. And basically, we stored data in 8K pages, and each page holds data of one row or more. The data was stored row-wise, and this means that if I have 20 columns in the table, all of those columns will be on the same page. Of course, we also have other allocation units like log data and row overflow data, but generally speaking, the data is stored row-wise. In Columnstore, each page contains data of a single column as opposed to a single row. And since there is a lot of repeatability in column values, the data can be highly compressed. Let's say I store data of all of the states in the United States. So let's say we have 300 million people in the States. So we will have, let's say, 50 million in California and 20 million in Texas and 30 million in New York and so on and so on. So the values are repetitive for the state column. So if we compress that and store the data in a much more efficient way, we can store much less data than we need. So as we said, that is because of repeating values and some additional tricks that we will see next in the presentation. Because we compress the data, more data can fit in memory. Let's say we have 128 gigabytes of memory. Instead of storing, let's say, 20 million rows in memory, we can store 100 million rows or 200 million rows or a billion rows, because the data is stored in a much more efficient way. Each column is also fetched independently. Let's say I want to get only some of the columns of the table. In the traditional approach, I would have to read the data of all of the pages that stored the columns that I don't need. Of course, we can use covering indexes, and we will see a demo about it. But generally speaking, if we have a lot of columns in the table and we can't cover all of the queries that use all of the columns, it becomes a problem. So Columnstore deals with this kind of situations much better, and we will see in a demo later in the presentation. And all of those things can dramatically decrease the I/O we perform on our system. So some terminology about Columnstore. A row group is 1 million rows, and basically the 1 million rows and the data of all of those rows. Basically, a row group is composed of all of the columns that store 1 million rows of the table. And a segment is a unit inside this row group that stores data of a single column. So generally speaking, we will have 1 million rows and 1 million values in a segment. And each segment can store data of between 100,000 rows to 2 million rows. And we will talk about when it will store 100K rows and when it will store 1 million rows. Generally speaking, we strive to get 1 million row segments and not 100K segments, because this is better in terms of higher consumption. Each segment is compressed independently and is stored as a separate lob object. And the segment is the unit of transfer from disk. Each time I fetch a column, I read all of the whole segment. I don't read the separate pages that compose this blob. I read the whole segment. Another thing we cut in Columnstore is batch mode processing, and this is one of the biggest advancements in query processing in the last few years. The data is processed in vectors of 1,000 rows. This means that we don't work row by row, but we work in vectors. And if someone learned linear algebra in university, I sucked at it. I hated it, but I guess it's good for Columnstore. So this is how it works. The data is manipulated in the CPU L1 cache. So if you work with Columnstore, you want your L1 cache to be as big as possible. As we said, it's much more efficient than row by row because we use mathematics and CPU. And we have better parallelism and better algorithms for processing data. And this is what we want to see in the execution plan when we work with Columnstore. We want to get an estimated execution mode of batch and actual execution mode of batch. If we get a row execution mode, this means that we work row by row and the query will be processed much slower. In SQL Server 2012, we had some gotchas. We could use only non-clustered column store. We will soon talk about what is clustered column store, but the non-clustered column store means that we have a regular disk-based and row-based table, and we build a column store index on top of it on some of its columns. Once we did that, the table became read-only, not updatable, and this was bad because it was much harder to work with the table, but we could bypass that by using partitioning. So most of the table is partitioned, and let's say we work with daily partitions. We load the data into the last day partition, and at the end of the day, we would switch this partition in, and that way we could bypass the problem that the index is not updatable. And we also used union all to union between the old data that is compressed in Columnstore and the new data that sat on row-based table and was updatable too. So even though the table wasn't updatable, we could bypass that. The bigger problem was that it was how to get batch mode processing. If you didn't work with pretty simple queries, you didn't get batch mode processing, and you would get row by row processing, and the queries went much slower. SQL Server 2014 is much better, and we have a new feature called clustered column store index. As opposed to non-clustered column store in 2012, the table is stored only as clustered column store. Okay? We don't have other indexes, we don't have a heap, we don't have a clustered index. The data is stored only in the clustered column store, and this means that we use our IO subsystem much better, as we store much less data. We don't have to duplicate the data between, say, clustered index and the non-clustered column store. It's updatable, but as you see, it's between quotes, and we will see in a minute why it's inside quotes. Basically, we can insert data, but it's not going straight into the table. It's going to a separate object called delta store, and only after certain things happen, it's compressed and inserted into the column store. And we say that in a minute. It's much easier to get batch mode, which means queries run much faster. And as I said, there are significant space savings because we store the data only as a compressed data and in the cluster column store. And you can get even more compression using something that is called archive compression. And this just means that when we write the segment back to disk, we just zip it a little bit more. The gotcha is that no other index is allowed, so you can put non-clustered indexes. You don't have primary keys, you don't have foreign keys, you don't have constraints, you don't have anything. So this is a problem in terms of data consistency that you need to take into account when working with Columnstore in SQL Server 2014. So it's kind of consistency against performance, and you have to balance that. As we said, no constraints, and this is pretty easy to create. Create clustered column store index, name of the index on your table. And that's it. You wait, you drink a few cups of coffees, and you have a column store index, clustered column store index. So how is the column store index built? So let's say we have a table. We start with separating the table to row groups. Each row group, as we said, will be 1 million rows. So we first split it to 1 million row groups, and we then split the row groups to segments. As we said, each segment holds data of 1 million values of a certain column, and then we compress. So let me just say that I'm not for compressing kids unless they really deserve it. So we compress the data, and how do we compress the data? Here are a few examples for compression algorithms. So the first algorithm is called value scale. We have a base and a value. So let's say you want to translate the height to heights that we can store more efficiently. So height of 180 centimeters will be 30, and height of 175 centimeters will be 25, and so on and so on. And our base in this case is 150 centimeters. So this is one way to compress the data. Another way is a bit array. So let's say we take this array of names, we can store the data in a data structure called a bit array and just light up and the bits for the values that are relevant to the row and turn them off when they don't relate to this specific row. In this way, we can represent a lot of rows in a very efficient data structure. Another way is to use something that's called run length. So let's say for Michael, I hold the value 3 because it is shown 3 times in the array. For Guy, I hold 1. For Maria, I hold 1, and for Matan, I hold 2. Another way is something that is called dictionary orders. So what this basically does is kind of normalization, if we can call it that way. So Michael will get ID of 1, and Guy will get ID of 2, and Maria 3, and Matan 4, and then we just store the IDs. And instead of holding data of text values, I use data of integers, which need much less space in our I/O subsystem and in memory, of course. And there are also other very cool algorithms, and you can read about it more in Nico Neugebauer's blog, and we will also talk about it in the resources section at the end of the presentation. How is insert implemented? We talked about querying, we talked about built-in. How is insert implemented? As we said, rows don't go straight into the column store, but when we insert rows, they go into an object called delta store, which is an unindexed heap. It's just a heap, regular row store table, but it doesn't have any indexes, no clustered indexes and no non-clustered indexes. And if you get to a situation where you have a lot of rows in that delta store, you can get to a situation where you query the table, but actually you go to read a lot of data from the delta store, and it's not indexed, and it can hurt. So we will talk about some optimization for that in a minute. So as we said, the data goes into the delta store, and every so and so minutes, there's an object that is called the tuple mover that wakes up and moves the data into the column store. Now this tuple mover is a very lazy guy. It wakes up only every 5 minutes, and it works with a single thread and moves only one delta store at a time. It searches for delta stores where they have 1 million rows, or to be more accurate, 1 million rows and 48,000 rows. And only for those delta stores, it compresses them and moves them into the column store. So let's say you load a lot of data, and let's say something like 100 million rows. It will take some time for these 100 million rows to get into the column store, and you have to use other methods, and we'll talk about it. How is delete implemented? Let's say we issue a delete against the column store, so this delete is not actually performed on the column store, but against some kind of array that is called the deleted bitmap. So for when a certain row is deleted, it's not deleted from the column store, but marked as deleted in the delete bitmap. And when we query the table, we have to read both from the column store and the delete bitmap in order to know whether this row is deleted or not. How's the update implemented? Pretty simple. We delete the row on the delete bitmap, delete the old values of the row, and insert a new instance of the row into the delta store. and it will get back into the clustered index when there will be 100 million rows in the delta store, and the tuple mover wakes up and grabs it and compresses it and moves it back into the column store. How's column store rebuilt? When we issue an alter index rebuild command, the column store will be rebuilt, and the process is that the column store will be rebuilt, but beforehand, SQL Server will go to the delete bitmap, read which rows are marked as deleted, physically delete them, and then rebuild the column store. So as we said, it recreates the clustered column store index. And one optimization we can use is to use max.1 to improve something that is called segment elimination. One of the optimizations with column store index is something that is called segment elimination. And SQL Server holds metadata information about the minimum value and the maximum value of each segment. And it can use that in order to know which segments he has to read for a certain query and which segment he doesn't have to read. So if we rebuild the column store, generally speaking, SQL Server will strive to get as much CPU cores as it can. But the problem is that each CPU will get data of rows from all of the ranges, and this can hurt segment elimination. So the column store will be built more quickly, but queries can hurt a little bit after the column store is rebuilt. And one thing we can do is to rebuild the column store with max.1. By the way, we can also rebuild the column store online, but of course, we have to pay with resources for that. Another thing we can do for further optimization is to build the column store, the clustered column store, on top of a clustered index for better segment elimination. We don't have an option to control the order of the column store built, but what we can do, let's say we have a table with an ID column, and we know that we will filter on this ID column a lot. So what we can do is we can build a table with a clustered index on the ID column, and then build the column store on top of this table. So the column store will keep this order when it's built, and that way our column store will be ordered according to this ID column, and when we filter on this ID column, we will have good segment elimination. But for best performance with select queries, you need to build the column store on top of a cluster table and use max.1 in order to make sure that there are no intersections between segments because of parallel build. Alter index reorganize, it only compresses the closed row groups and moves them into the column store. So it's not like regular index rebuild. It's a whole other story. It also only compresses the closed row blocks, which means that they got to 1 million rows, and get them into the column store. So let's say, let's talk about the situation we've been in before. We loaded 200 million rows, and all of them are inside the delta store. We can call alter index reorganize, and all of the rows will be compressed and get into the column store as soon as possible. Another thing we can do is to use the option called compress all row groups to compress all of the row groups and not only those ones that got to 1 million rows. And as we said, use it when the tuple mover can handle the load, because as we said, he's a pretty lazy guy. So why is Columnstore so fast? So we talked about compression. The data is stored much more efficiently, both on disk and in memory. So even when we have to go to disk, and disk is the slowest part in every computer system, we grab much less data than we needed in regular row-based tables. And also, a lot more data can fit in memory, and then we read the data much faster, and we also read the data faster from memory because it's compressed so well. We also have batch mode, which is much faster than row-by-row operations, as we said. We only grab the needed columns, and we have segment elimination and improved I/O operations. And what I mean by that is that even if we need to go to disk, as we said, we read much less data, and even the data we read, we can use an aggressive read-ahead algorithm that reads the data much faster. The read-ahead is a mechanism in SQL Server that says, let's say I have to read data from disk, and I read the rows 1 to 1000. So SQL Server assumes I need to read the rows of 1001 to 2000 also. So it will use an algorithm, a mechanism called read-ahead to read those rows too. But in regular row-based tables, the read-ahead is only 512Ks at most. And in Columnstore, excuse me, I think it's 64K, not 512Ks, but anyway, in Columnstore we can get to 8 megabytes of read-ahead. So each read-ahead can read much more data, and we can get data into memory much faster, and all of the I/O operations is much more efficient. So what Columnstore is good for? So Columnstore is good for big aggregation of fact tables, where we read a lot of data, and we read a lot of data from many columns, which are hard to cover using regular indexes. And another attribute of aggregation of fact tables is that there are many repeated values in the tables, and those will be compressed well using the compression algorithms Columnstore uses. And as we said, it's good also for wide tables. We can't cover all of the columns for all of the queries, so this is problematic in row-based tables, and much better in Columnstore. Columnstore handles it much better. And as we said, tables with many repeating values and low change rate. And by low change rate, I mean that we don't have to update each and every row many times. In that case, maybe it will be better to work with row-based tables, because the updates for row-based tables are generally faster than Columnstore. You generally don't want to use Columnstore for an OLTP system, even though you can always find the use case for that also. So we talked a lot. Let's see a demo. And meanwhile, Jeff, are there any questions for now before we dive into the demo?
Yeah, so just one quick one that seems applicable here. Somebody asked, does a Columnstore require an enterprise version of SQL to take advantage of?
Unfortunately, yes. Yeah, okay. Unfortunately, most of the cool features in the last few years are enterprise edition only, like a Columnstore, like in-memory LTP, and other stuff.
Okay, and then we'll do one more question quick. So there was a question early on about batch mode processing. How is it just that better overall from a performance standpoint?
So, so because the data is handled in vectors of 1,000 rows, and we don't have to manipulate each and every row separately, it works a lot better because we work in batches that are not too small and not too big for the CPU to handle that, and that's the main reason it's much faster. And it also uses some very advanced algorithms that were developed since the old traditional data structures were developed in the 90s, because the computer world has advanced since the 90s, and Columnstore is one of the technologies that uses those advances. I hope that answers the question.
Okay, sounds good. Thank you.
Cool. Okay, so let's start with the demo, and for a start, let's show the sizes of tables. So what I have here is a table called fact internet sales big, and it holds about you know what, I actually forgot, but we see using SP space used how many rows we have. So we have 120 million rows. I remembered correctly, actually. So for the fact internet sales big, we have a reserved of about 23 gigabytes, or 16 gigabytes of data. And for the Columnstore, we have only 1 gigabyte of data. So this is the compression. As we said, data is stored much more efficiently because of repeating values and compression algorithms and so on and so on. So very easily, we saved about 90% of the data in the table. And let's start with showing some queries. So what we have here is a typical data warehouse query. We have a top 1,000 and some sums and the group by. And we first go to the fact internet is big and the dim product big dimension, and we run that. And it runs pretty fast. It runs in about 3 seconds, and the reason is that I created a covering index that will cover the query, and it holds the product key and unit price and freight and tax amount, and sales amount, and the total product cost. So if you have this kind of table and you have a small set of predictive queries, you can do pretty good with regular disk-based tables also, and covering indexes. And let's take a look at the Columnstore. And it worked pretty well too. Now what happens if we add another column that is not covered in the index? We'll go to the non-clustered, to the non-Columnstore table, to the regular table. And we will have to wait a little bit, because as we said, the last column is not covered in any index, and we have to read a lot of data from the table itself, from the non-clustered index, and we got to a situation where the query ran for 14 seconds instead of 4 seconds. What happens in Columnstore? When we add another column, it handles it much better, and we got the data in only 1 second. And so of course the data was cached, but the data of the revision number was not cached, and we had to get it from disk. It was very, very fast. So as we said, Columnstore handles non-predictive situations and non-predictive columns much better than regular tables. And it can be even better if you use the table called fact internet sales big Columnstore ordered. And what I did here is I created the table on top of a cluster table, And I did that, as we said, in order to increase segment elimination. So let's see if it works. And we clear the cache, and it worked in 5 seconds. And actually the reason is that originally I built a table on top of clustered Columnstore, but since then there has been some changes, and the data got a little bit dirtier. But generally speaking, if you make sure to build a table using on top of a cluster table and using max.1, what you will see here is that the mean data ID will be, let's say, 1 to 1000. The mean data will be 1 and 1000 here, and 1001 and 2000 here, and so on and so on, and you will get very, very good segment elimination, and you will see that in very big tables and very big queries. Now let's talk about inserts, and I will increase the font a little bit, and we'll see how we insert data into Columnstore, and I will do that in a transaction. So first off, I will insert 1 million rows into the Columnstore table, and we will then take a look at the DMV core SysDM Columnstore row groups, which shows all of the row groups and the delta store and their state. So we'll wait a few more seconds. And a few more seconds. This is 1 million rows. Okay, and now let's look at the sys.columnstore row groups table, and we can see we have one open row group that has 1 million rows, and this is our row group. All of the other row groups are compressed, and this means that they are not in the delta store, but in the column store itself. What we will do right now is insert an additional 50,000 rows. And now we can see that we have one open row group, but the total rows in it are not 1 million, but 1,424 rows. And this is the remainder of the threshold for closed row group. And we will search for this closed row group. And where is it? There it is. So we can see we have a closed row group of 1 million rows and 48,000, and this means that the row group is closed and waiting for the tuple mover to compress it and insert it into the column store itself. Now, inserting 1 million rows into 148,000 rows into the column store, it still doesn't get it into the column store itself. It still goes into the delta store. If you want to bypass the delta store and the tuple mover, you have to use bulk insert. And with bulk insert, you can use chunk sizes of 100,000 rows and up. And that's why we said at the beginning of the presentation that a row group can have between 100,000 rows and 1 million rows in it. So now we will check again, and then we see we have an open row group, and where is it? And oh, sorry about that. We inserted the right amount of rows into the delta store. It's a closed delta store, but it's not a compressed delta store. It's in the delta store, but it's not inside the column store. And now what we can do is we can run alter index reorganize, and then the closed row groups will be compressed and inserted into the column store. Now let's talk about another scenario. And what we have here is just a small table that is called website hits. And it's just here to show proper database design in Columnstore. So it's a table called website hits, and it has a website address and a date and number of hits. And I inserted data from 1975 until a few months ago. And I created a clustered column store index, and I also created a dimension with an ID column and the website address, and inserted the data. And now let's look at a few options for getting the data, for getting the sum hits of Google. So we will light up statistics time and statistics IO and clear the cache, and let's look at it. So first off, we will query the column store and look for the Google hits. And what we see here is that we have a column store index scan here, and then we have a filter, and this filter is filtering the data in order to get only the Google hits. So the problem here is that we go to the column store, read all of the data from disk, all of the 212 million or something like that rows, and only then filter the data in memory. We don't filter the data here on disk, we filter the data in memory. And the reason is that Columnstore doesn't perform the action that is called predicate pushdown for text columns. If we had predicate pushdown, we would filter the data here in the Columnstore index scan. But since we don't have predicate pushdown, we have to filter the data here, and it's less efficient. And we can see here that we read some data, and then the elapsed time was this time, and the CPU time was more than 2 seconds. Now let's look at another option, which is to use the dimension column, the dimension table, and we filter the data from the dimension. And when we do that, we will get a different execution plan. We do an index seek. We get one row from the dimension. We distribute the streams in parallelism, and then read the data from the column store. And when we look at the execution times, we can see that the CPU time went to much less. Instead of more than 2 seconds, it went down to almost half of a second. And of course, the most efficient way to work is that, let's say we know that Google has the website ID of 2, we filter the website ID of 2, and then we filter the data in a much more efficient way, and the elapsed time went down from more than 2 seconds to less than 300 milliseconds, and the CPU time went down also. So this is a little bit about Columnstore demo. And what I wanted to emphasize here is that Columnstore is not a magic solution for bad design or bad code. It's true that if you put your big tables on Columnstore, some of your queries can run much faster, but some of your queries can run slower too. So this is not a magic solution, and you still have to take into account database design and write efficient code and all of the best practices we knew as DBAs for use. Regarding predicate pushdown, the one thing we talked about with text, there will be predicate pushdown in SQL Server 2016, but it will be only for char and n-char columns. So if you work with variable length textual columns, it will still not help you. So SQL Server 2016 will be better. We'll talk about it in a bit, but still, it's not a magic solution, and we still have to work with good database design and good code. So when you go to work tomorrow and start playing with Columnstore, how do you make your benchmark successful? So as we said, don't neglect database design. You will probably still work with a fact dimension model, and the fact table will be composed mostly of integer columns, and it won't be very wide in the sense of storage. It can be wide in the sense of number of columns, but it shouldn't be very wide in the sense of storage and text and so on. Don't rely on the tuple mover. As we said, it's very, very lazy. So if you insert a lot of data into delta stores, don't rely on the tuple mover and use alter index reorganize in order to insert the data as soon as possible into the column store. But actually, if you load a lot of data, don't load the data into the delta store, but use bulk insert in order to bypass the delta store and insert the data straight into the column store, and use partition switch in order to do it even more efficiently. And also, don't delete the data using regular delete operations, which will move the data and mark the row as deleted in the delete bitmap, but delete data using partition switch. And if you use only bulk inserts and delete using partition switch, you will get into a situation where you barely need to rebuild the column store and reorganize it. And that's the best way to work with column store, if possible, of course. It's not always possible. And partitioning key helps in segmented elimination. So let's say you build your column store on top of a clustered index. So you will get a column store that is ordered by one column, and it will help with segment elimination. And if you use a partitioning key, you will have another column that helps eliminate a lot of rows as a metadata operation. Another thing to take into account in your benchmark is the new cardinality estimator. Even though clustered column store is a SQL Server 2014 operation, and the new cardinality estimator is a SQL Server 2014 also, feature also. In some situations, the new cardinality estimator will be better, and in some situations it will be worse. So it's true for regular row store table, and it's true for column store tables also. So for your queries, you need to test both cardinality estimators and decide which is better. And you can control, using a trace flag, you can control which cardinality estimator to use if for some queries the old one is better and for some queries the new one is better. So what about high-bit scenarios? Let's say you have situations where you need to read a lot of aggregated data, and in some situations you need to read and execute very, very specific and point-based operations for very specific keys. So we have a few options. One of them is non-clustered column store. So let's say you have very specific columns in which they benefit from column store, but the rest of the columns are read better using regular row store tables, you can use non-clustered column store on top of a regular row store table that will use regular indexes, which are generally better for cases where we need very specific rows. Let's say select star from table where ID equals 1. It will generally run faster on row store table than column store table. So the problem with this one is that it's not so earlier, we can bypass this gotcha. Another thing you can do, I don't necessarily recommend you do that, is to put an index view on top of a clustered column store table. So you can build your column store table and get very good execution times for reporting type queries, but for point lookup queries, you will use the indexed view. The problem with this is that it makes all of the operations very, very slow, so you can check that, but generally speaking, it's not the very best practice to use this one. And there's another scenario, which is to use a regular table side by side with the clustered column store table. And some queries will go to the regular table, and some queries will go to the clustered column store. The point lookups queries will go to the regular, and the reporting queries will go to the clustered column store. And if someone says that we basically duplicate the data, I will say that we've been doing this for years. Because for years we had the raw data table, the OLTP type tables, and we had the aggregation tables. We aggregated the data and then queried it. So this is basically what we do here. We don't duplicate the data, we just use it for in different ways. So up till now we talked about SQL Server 2014. Let's talk about SQL Server 2016, which will go out hopefully Q1 next year. I don't really know, but I hope this is the case. So in SQL Server 2016, we will have many performance improvements. One of them is predicate pushdown for textual fields. Another one is aggregate pushdown. SQL Server will hold inside the storage engine, we hold the max values and the average values and so on and so on. For most of the aggregation, of the mostly used aggregation functions, it will hold the data inside the storage engine and will make the operations much faster, even faster than they are today, and they are fast. And there are many other performance improvements too. In SQL Server 2016, you will have the option to use regular indexes on top of the clustered column store index, and this can be the hybrid scenario. You will bring your reporting type queries to the clustered column store, and your point lookups queries will go to the index, which is built to the regular index, which is built on top of the clustered column store. You will have the options for constraints on clustered column store, which is basically the same thing because constraints are implemented using indexes, constraints and primary keys, and so on and so on. And you will also have the option for updatable non-clustered column store. If you have a regular table, you can have one updatable non-clustered column store on top of that. And this is again another type of hybrid scenario, and you'll have the option to select which hybrid scenario you want. If your table is generally more LTP style, you can use a regular table with updatable non-clustered column store on top of that. And if your table is generally reporting style table, you will work with a clustered column store and regular indexes on top of that. So you will have to know your data and of course benchmark and see what's best for you. And you also have the option for column store on top of in-memory LTP, which brings together two of the most neat technologies in SQL Server today. and you will have the option for many kinds of streaming data, reporting, and so on and so on, and the sky's the limits, and it's very, very, very cool. What about the future? Perhaps in SQL Server 2016 and maybe afterwards. So I really want to see a rebuild with an order column, so we don't have to build a table on top of a cluster table in order to do that. And another problem is that if we build a clustered column store, we lose the ordering that we got because of building the column store on top of a clustered table. So I really want to see a rebuild with order by some column. And I say probably next version because one of the reasons I said at the start of the presentation that Microsoft invests in this feature a lot is that they fix bugs. They don't tend to fix a lot of bugs that you issue in Connect, but they do fix bugs in Columnstore. And Nico Neugebauer opened the bug on this specific thing, and Microsoft said they will fix it. So hopefully there will be, and I start talking faster because we're at the end of time. So segment maintenance, during the segment maintenance and the tuple mover and alter index reorganize. I really want to see merge of segments and deletes, and it should be in the next version. Segment elimination info in execution plan. It's already up in Azure SQL Database and will probably be in SQL Server 2016. And I really want to see batch mode for row store and indexes on Delta stores. So in case we have a lot of data in the Delta store, the querying of the Delta store will be faster. I really want to see a more than one column store index on table for better segment elimination and for better ordering, and not so lazy tuple mover or tuple movers in general. So resources, the absolutely best resource on Earth and in the universe is the Columnstore series of Nico Neugebauer's. The last time I checked, Nico had 61 posts for Columnstore, and this is a truly amazing resource, and go ahead and read it. And he also has a few presentations at SQL Bits, and the 24 Hours of Past SQL Server 2014 edition. Sunil Agarwal and Jimmy May gave some great sessions, and go ahead and watch them. And thank you very much, and in case you have some questions, I'll be happy to answer them.
So this is Jeff. We're at time. There was one quick question. A person was wondering if they could get a copy of the scripts that you went through earlier in the presentation.
Yes, of course. I will post it in my blog at manderasql.com/blog, and I will also send you guys the scripts in order for you to be able to post it on the performance chapter site.
Okay, so thank you very much. I will send you a few more questions that came up during the session, and I'm assuming you could just answer them directly.
Great.
So, all right, thank you for your time. Thanks for attending the session, and hopefully we'll join other sessions today. Thank you, guys.
Okay, thanks, guys. Thanks for having me. Bye-bye.